So now we need to go ahead and take a look at the energy considerations of the cyclohexane conformations. So I mentioned in the last video that the cyclohexane ring, rather than lying flat, will adopt what's called a chair conformation. And the reason for doing so was to minimize angle strain, because the angle can get very close to 109.5, which is the ideal for a tetrahedron. And then also, if you look in the picture on the right, I've held up the cyclohexane ring in the chair form so that you can look down a carbon-carbon bond. And now you should notice that if you were to draw a Newman projection of this, that everything is staggered. And so you have alleviated that eclipsing that was taking place whenever it was lying flat. In reality, there are two possible chair conformations. You could see the one on the left where you have this end up and this end down, or you have the one on the right where you have this end up and this end down. And what's actually going on is that cyclohexane will exist in an equilibrium that's rapidly interconverting between these two different chair forms. And we're going to arbitrarily call these chair 1 and chair 2. I could have just as easily as called this one chair 1 and chair 2. It doesn't matter. But just to signify that there are two different possible conformations. The way that it goes from chair 1 to chair 2, hopefully you saw in the video where I interconverted between the two different chairs. It doesn't go directly from here to here. It goes through this intermediate step that's called the boat conformation. Let's take a look at this boat conformation. So it's called a boat because it kind of is shaped like a boat, right? And you have these interactions that are taking place here that are called flagpole interactions. Flagpole, where you can get a little bit of steric interaction there, especially if those were larger than hydrogen. You also, if you look down the carbon-carbon bond, will see that everything is eclipsed. So if you had to guess, hopefully by now you'd be able to tell me if I said, is this a high energy or low energy conformation? You would probably say relatively high in energy. And if we were to sort of draw these out in terms of relative energy, the two chairs are equal in energy, but there's this boat that they have to go through to get from one chair to the other that's higher in energy. And the barrier there to go from chair 1 to chair 2 is 30 kilojoules per mole, because it does have to go through the high energy boat conformation. At equilibrium, cyclohexane exists as a mixture of equal molar amounts of chair 1 and chair 2. And so you would have, if you measured at equilibrium, about a 50-50 mixture of the two different conformers at any given time. Something that I want you to notice going from chair 1 to chair 2 is that if you take a look at the carbons that are red in chair 1, you see that they're all kind of in the down position. And if you look in chair 2, those same carbons are kind of pointing up in up positions. If you take a look at the black carbons on the left, you see that they're pointing sort of up, and in chair 2 on the right, they're pointing sort of down. So it seems like when it flips from one chair to the other, that all the carbons that were up go down and all the carbons that were down go up. And indeed, that is what happens. Something else notable that takes place when flipping or interconverting between chair 1 and chair 2 is that if you take a look at the position of the atoms, on the left side you see that the the red atoms that are connected to the black carbons are sticking straight up. And if you look at those same atoms on chair 2, they're sticking off to the side. And you could do the same thing with these white atoms on the red carbons that are sticking straight down. If you look at them over here, they're sticking off to the side. And we could do the same thing with the atoms that are off to the side on the left. They now, if you track them over here, are sticking straight up or straight down. When atoms are pointing either directly up or down on the cyclohexane ring, like the ones I'm highlighting in purple, we say that those atoms are in the axial position. When the atoms are pointing off to the side, like the ones I'm highlighting in yellow, we say that these are in the equatorial position. So notice something key that happens when the chair interconverts from the first chair 1 to chair 2. All of the atoms that are equatorial become axial, and all of the atoms that are axial become equatorial. And so that's going to be a key feature of any chair interconversion. This type of axial to equatorial, equatorial to axial shift will always take place.